نبينا محمد وعلى آله وصحبه أجمعين. This is section 8.3, estimating a population proportion. In the previous section, we discussed how to find a confidence interval estimate when the population of interest was the mean. The population mean. We mentioned how to find the confidence interval for the population mean. Well, sometimes we need to talk about the proportion of items in the population. So, for example, you may wish to estimate the proportion of customers who are satisfied with the service provided by your company. So you need the proportion, not the mean. So the population proportion is denoted by P, as we know. And the point estimate for P, which is the population proportion, is the sample proportion, which is P bar. And if you remember, P is capital X over capital N. That's the population proportion. And the sample proportion, P bar, is small x over small n, where small x is the number of items in the sample with the attribute of interest, and small n is the sample size. So if you want to find the proportion of Arab students in the class, you can divide X, the number of Arab students, by all the students in the class. You get the sample proportion. In chapter 7, we introduced the sampling distribution for proportions. And we said that if sample size is large, if NP is greater than or equal to 5, and NQ is greater than or equal to 5, where Q is 1 minus P, then the sampling distribution can be approximated by the normal distribution. And we said that we can change the distribution of P bar then to Z using this formula over N. We studied this in chapter 7. So the standard error for P bar in chapter 7 was this quantity, square root of P times Q over N, where Q is 1 minus P. Now, we usually, if you remember in 8.1, we use how to find the confidence interval for P, the population proportion. We need the point estimate plus or minus the critical value times the standard error times the standard error. That's the general formula to find the confidence interval for any parameter. So the point estimate here for P is P bar, and the critical value will come from Z table, and the standard error is sigma P bar, which is this one. But we need to estimate P, the population proportion P. We need to estimate P, and we don't have it, okay? We don't have it. So we cannot find the standard error using P because P is not given, is unknown, okay? We need to estimate P. So what can we do? We can estimate the value of the standard error by substituting P bar for P, because we know P bar would be given in the question, okay? Provided that N P bar is greater than or equal to 5, and N times Q bar is greater than or equal to 5. So we will use the standard error of P bar in terms of P bar instead of P, because P is unknown. So this would be our standard error for P bar times Q bar over N. And then the confidence interval for P would be P bar, the point estimate, plus or minus the critical value times the standard error for P, which is this one, for P bar. So that's the confidence interval. This is the critical value. This is the standard error. And if you multiply the critical value times the standard error, you get E, or the margin of error. So it's P bar plus or minus E, where E is the margin of error. So the critical value will be here taken from the Z value, because if NP bar is greater than 5, NQ bar is greater than 5, we can approximate using the normal distribution. That's it. That's the first formula in the section. And let us solve an exercise. Compute the 90% confidence interval. If you remember in 8.1, if 90% is the confidence interval, the confidence level, 90%, then the critical value is 1.645. You can find that from the Z table by dividing 90 by 2 and search for 0.45 inside the Z table, or you can use the T table, look to 90% column and go to the last row. It is 1.6449, or I can just use 1.645. So that's the critical value. Compute confidence interval estimate for the population proportion. So that's a similar question. We have similar question in 8.1, but the only difference, population mean instead of population proportion. So you have to read the question carefully, and also the given information will help you. Here we have the sample size, which is N, and the sample proportion is given. So P bar is 0.4. So we can immediately find the confidence interval. It would be, the formula says the confidence interval is the point estimate plus or minus Z times P bar times 1 minus P bar over N. That's the confidence interval. So P bar is 0.4 plus or minus Z is 1.645 times square root of 0.4, which is P bar, times 1 minus P bar, which is 0.6, over N, which is 100. And this is equal to 0.4 plus or minus the margin of error. And we can calculate the margin of error using the calculator. So 0.4 times 0.6 over 100 under the square root times 1.648. This is just 0.081 when you approximate to 3 decimal places. So the confidence interval would be 0.4 minus 0.081, which is 0.319, between 0.319, and if you add 0.4 to 0.081, you get 0.481. So this is the confidence interval for the population proportion P. You can say that P is between 0.319 and 0.481. So we used the sample proportion to estimate the population proportion, and we are 90% confident that the population proportion will be between these two numbers under this given information. You can try this one. It is similar, very similar. Also this one, only the confidence level is different. Okay. And let us solve this question. A random sample of 200 items, so this is N, reveals that 144 of the items have the attribute of interest. So this is in fact small x. What is the point estimate for the population proportion? The point estimate for P, the population proportion, is P bar, which is defined by x over n. So it is 144 over 200. So that's the point estimate of B. The answer is 0.72. So P bar is 0.72. Use the information from the random sample to develop a 95% confidence interval. So Z is 1.6 0.96. Estimate for the population proportion of all items having this attribute of interest. We need only here P bar, and we have it. It is 0.72. So the confidence interval would be P bar plus or minus Z times P bar times 1 minus P bar over N, and it is 0.7. 0.72, alhamdulillah, plus or minus. Z is 1.96 square root of 0.72 times 1 minus 0.72, which is 0.28 over N, which is, what is the sample size? 200. N is 200. And similarly, similar to the question we solved, you can find the margin of error and then determine the confidence interval, the 95% confidence interval for P. Please try to solve this exercise similarly. And also, let us solve this one, 853. A random sample of size 150, so this is N, taken from a population yields a proportion equal to 0.35. So this is the proportion of what? Of the sample. So this is P bar. Determine if the sample size is large enough so that the sampling distribution can be approximated by the normal distribution. We said it will be large if N times P bar is greater than or equal to 5 and N times 1 minus P bar is greater than or equal to 5. So you have to check this. Of course, 150 times 0.35 is greater than 5. It's 52.5, so it's greater than 5. And also 150 times 1 minus 0.35, which is 0.65, is also greater than 5. So yes, it is large enough. Construct a 90% confidence interval. You can solve this question similarly. Interpret the confidence interval. You can say that we are 90% confident that the population proportion lies in the given interval. Produce the margin of error. Remember that the margin of error is Z times square root of P bar 1 minus P bar over N. So it is already calculated here in part B. It would be calculated in part B because the formula for the confidence interval is P prime times Z 1 P bar times 1 minus P bar B bar plus or minus Z times over N. And this is in fact is E, or the margin of error. Okay, this is the first part. Now the second part in section 8.3 is to determine the sample size, the required sample size to estimate or for estimating P, the population proportion. So this is the margin of error, as we mentioned, okay? But we don't have P, so P, if not given, we will use just P bar, okay? So how to find the sample size? Well, you can write this as E equals Z times square root of P1 minus P over square root of N. Okay, you can distribute the square roots. And then you can interchange, okay, the position of E and square root of N. So square root of N, because we need to find the sample size, is Z times square root of P times 1 minus P over E. And then you raise to the power 2 to get N. So you will get N equals Z square. And if you square the square root, you get rid of it, P times 1 minus P over E square. So this would be the formula to find the sample size. You need Z, the critical value, you need P, the population proportion, and you need E. But the population proportion is not available because we need to estimate P. So what to do? We have two choices, two methods. First, we can select a pilot sample and compute P bar and use it instead of P. That's one method. As we did in section 8.1, we select a pilot sample and we calculate S and we use it instead of sigma. Here, we pilot sample, select a pilot sample, compute P bar, use it instead of P in the formula. So you will use here P bar. If you have a pilot sample, well, if there is no pilot sample and you don't have P bar, so you can select P 0.5. You can choose P always if you don't have a sample 0.5. Why 0.5? Because if you replace P by 0.5, then P times 1 minus P would be 0.5 times 1 minus P, which is also 0.5. So 0.5 times 0.5 would be 0.25. This would give you the maximum value, the greatest value for P times 1 minus P. The greatest value. So you are in the safe side and you will find the N, even it would be a generous N here. You will find the suitable N, okay? Because you chose the greatest value for P times 1 minus P. If you choose 0.4, for example, 1 minus P would be 0.6, 0.4 times 0.6 would be 0.24. So if you choose 0.5, done, okay? You can get N. So you have two choices. Either pilot sample and use P bar instead of P, or just take P as 0.5. So let us solve exercises. A pilot sample of 75 items. So these are the items of the pilot sample. This is N of the pilot sample. And the number of items with the attribute of interest was found to be 15. So what is P bar? In the pilot sample, 15, which is X, over 75, which is N. This is P bar in the pilot sample. It is 0.2. So P bar is 0.2. And now you can use it instead of P. Okay. How many more items? The question, how many more items? Well, we chose already in the pilot sample 75. So we will find the required sample size and then we subtract the required sample size minus the 75 which we already chosen to answer this question. How many more items must be sampled to construct a 99% confidence interval estimate for P with margin of error equal to 0.025. So what is the formula? N, the sample size, we need the sample size, equals Z squared times P times 1 minus P over E squared. Okay, that's the formula. And Z, we need Z, the critical value, 99%. So I will use the T table, the last row. This is the 99%, 2.57. You can use 6 or 5.8. It is no problem. 2.576. I will use 2.576. So that's the critical value. So 2.576 squared. P, I will use P bar now instead of P. 0.2. 1 minus P bar is 0.8 over E square, and E is 0.025. So this will give me the required sample size. So if you multiply using the calculator, you get 1698.76. So the required sample size is 1699. You round up. If you remember, you need to round up. This is the required sample size. To answer his question, how many more items must be sampled? So 1699, which is the required sample size, minus the 75th items we chose in the pilot sample, and this will give you 1624 more items must be selected. That would be the answer of this question. Another question. A magazine company is planning to survey customers to determine the proportion who will renew their subscription for the coming year. Okay, so we need to estimate proportion here. The magazine wants to estimate the population proportion P with 95%, so Z is 1.96 in this case. Confidence and margin of error E is 0.02. What sample size is required? Well, we don't have P, we don't have pilot sample, so P prime, P bar is not there. So what we can do, we will use P.5. So N by definition is Z squared times P times 1 minus P over E squared. So Z is 1.96 squared times 0.5 times 0.5. 1 minus 0.5 is 0.5 over 0.02 squared. And using the calculator, we get the answer, which is 2401. Now, this answer without any point, so that's the required sample size. So N is 2401. This is the required sample size. That's the end of this section. All the other questions would be similar. This question is a nice question because it has the two ideas together. So let us do it. A survey of 499 women, this is N, revealed that 38% were flats to work. So this could be P, okay, P bar 0.38 because it's from a survey of 499. Use this sample or information to develop a 99%. We just have seen that Z in this case is 2.576 for 99% for a population proportion of women who wear flats to work. Okay, so what is the definition of the confidence interval? P bar, which is the point estimate plus or minus Z times P bar 1 minus P bar over N, and you just substitute. You have everything. You have P bar, you have Z, so you have N is 499, and find the confidence interval. That's the first part. The second part, suppose we also wish to estimate the proportion of women who wear athletic shoes to work with margin of error 0.01, so this is E, 95% confidence, so Z is 1.96. Determine the sample size required. So we need to determine the sample size required, which by formula is Z squared times P times 1 minus P over E squared. Well, we have E, we have Z, but we don't have P, and we don't have a pilot sample, so P bar is not there. So we just use P as 0.5 and find the required sample size. This is the end of section 8.3 and chapter 8 and stat 101.